but also sometimes my impression, because I used to work in quantum gravity for quite a few years, and my impression was that sometimes people take it a bit too light, saying that, oh, and then we have quantum gravity, so there is no causal structure. But I mean, come on, how can you not have a causal structure? You need to have some causal structure. It can be, well, effective or emergent or whatever, but I mean, you do have a causal structure if you're doing experiments, so you must have a mechanism which gives you that. So that's my somehow guiding idea, that you need to understand what this causal structure might be, and then look for nice mathematical structures which can implement it.
So yeah, at the bottom, there might not be a nice, well-defined, I guess what you'd call chronological time, but there still has to be some sort of causality, even if it is, as you said, effective or statistical or something. In the end, we know that something happens, and because of that, something else happens, right? And
Yes.
so much of that happens that we can actually assign these numbers to these numbers that we call, time or whatever we want to call it. I don't know if that's the best way to put it, but we can add some sort of metric to it and say this is a number here, that's a number here, even if that number might be a little bit different in this situation or that situation.
Yeah, that's right. So that's somehow, well, now we jump into the conclusions of this paper, but maybe it's a good timing for this to happen. Anyway, so our main message from this paper was that well, you can say that you have two levels of say conceptualization. So one is the effective level, and that's the level in which you do experiments and you gather data and well, you do experiments and have some outcomes, inputs, and whatever. And then you need to have some, well, you always have some notion of causality, you always have some notion of time, because if your detector clicks, then your data comes in an order, in a very specific order, whether you ask for it or not, and it doesn't depend which labels you put on them. It always comes in some sequence, right? And if you have multiple detectors, you have some effective notion of a space, because you know that these are separate things and this gives you separate data. So, well, you can call it whatever you like, but it's reasonable to say that, okay, they are space-like separated. So you have some notion of a space. Okay, so at least for this effective level, you need some notion of a space-time, in the sense that you have some notion of time, which gives you the ordering of this empirical events, and some notion of space, which can distinguish different data sets. And you have some notion of causality, which essentially pertains to the correlations of what you observe. Okay, then if you say that, okay, I have a limiting speed in the universe, let's say the speed of light, but if you don't like the speed of light, you can take whatever else speed if you wish, but there is a finite speed, then it gives you this notion of this defines you this cone structure and tells you which of the events can be possibly causally related with another and which cannot. Okay, and this is something that you always need to have at the experimental level, empirical level, or effective level, whatever you call it. And you absolutely need this to have experiments. Okay, and then, so that's let's say the upper level, and then down under you can have any crazy theory you wish, quantum gravity or whatever else, but you need to establish a link between the two layers if you want to make contact with experiments. Okay, so that's somehow the message. Okay, and we're saying that general relativity is really well suited to model the space-time structure of this effective layer.